Hi class, this week our lab is separation of components of a mixture. Mixtures are combinations of two or more components. In this case, lab flow refers to substances as components. They mean the same thing, but I am going to refer to everything as components. That's how lab flow wants it. Mixtures are combinations of two or more components in which each component retains its own chemical identity and therefore its own properties. So a mixture is much different than a pure substance. Let's cover pure substance first and then we'll go back to mixture. Pure substances have fixed compositions while the compositions of mixtures can vary. That means that pure substances like molecular H2O is always H2O. No matter where you find it, it is always a chemical makeup of H2O. If you see something that is not H2O, it's not water. For instance, if you find that the makeup is H2O2, it's peroxide. So pure substances always have fixed compositions. That's how you know what they are. They never change. Mixtures, on the other hand, can change, have a variable of composition. This is very similar to think of if you stick your hand in the sand at the beach. You may pull up shells, you may pull up sand, maybe a little crab, and but you stick your hand again in another place and it'll always vary. You'll never get the same amount of sand. You'll never get the same amount of anything else involved. Mixtures are, in a sense, combined together, but they're not interacting. They're just hanging out. They're not interacting. There's no changes taking place. They are just there in the same room. That is what mixtures are. And the mixtures, and there's two different types. Homogeneous, which is a solution. It's uniform in composition. A good example would be vinegar, which is made up of water and acetic acid. It's a mixture, but it's one, I like to call this one phase, meaning that you only see one phase throughout the whole thing. You cannot see the components that's made up of. Another example, sugar water. Sugar will dissolve into water and air. The air we breathe is a mixture of nitrogen, oxygen, a couple other things, water vapor, and so forth. But depending on where you are in the world, it could be different. The higher you go, oxygen will be, concentrations will be less. If you go to Vegas, the water vapor concentration will be much less than something like Seattle. Heterogeneous mixtures, this is what our lab is about this week. And it is components that are not uniformly distributed, but have a variable distribution. An example would be sand and water. I call these two phases, two or more phases, because you can see that it's not uniform and you can actually see the differences in the phases. So this would be one phase for homogeneous. If you look at cereal here, you got milk, you got, I think, cornflakes and berries. Blueberries? Maybe it's blueberries. This is three different phases that you can just visually see. Here we have, looks like oil, and I'm not sure what's at the bottom, but you can definitely see at least two phases. That is the difference between heterogeneous and homogeneous, an easy way to determine it. I also have these pictures here so you can understand there's a third one that really isn't discussed, but it does exist. So if you look here at A, this is heterogeneous. We can see different colors. They're different. You can call them phases, and you can count each one, and it would be many. Look at B, it's all blue. So this would be considered homogeneous. It's all uniform. You can't really say there's more phases than this. And then if you go to C, there's some yellow. Now it's two phases, but there's very small amounts of yellow. This would be an impure substance, where one of the substances in a mixture is greater than the amount of another one, significantly. So this would be something of an impure substance, and the other substance in it, which would be this yellow, would be considered an impurity. So the separation of mixtures. On top, I added what our mixture is made of. It's ammonium chloride, sodium chloride, and silicon dioxide, which is sand. So if you hear me say sand, it's easier than saying silicon dioxide over and over again. They all kind of look the same. So these are all mixed together in the mixture. If you were in the lab, this is what you would get in different percentages. Mixtures are characterized by two fundamental properties. Each of the substances in the mixture retains its chemical identity, and mixtures are separable into their components by physical means. What this means is exactly what I said prior. They are put together, but they are not interacting with each other. There's no attractions or minimal attractions. There's just nothing that's happening. They're just sitting there together in a room of strangers. And based on their own components, you can look at what salt, physical, look at what it does, what it can do, and based on physical properties, and you can figure out how to separate these from each other, which is exactly what is done in this lab. You want to make sure that you understand the physical components of it, because understanding that will allow you to use certain techniques that wouldn't work with other things, such as, for instance, water will dissolve salt, but it will not dissolve sand. So you want to make sure of those distinctions. You cannot use, for instance, a magnet on something like sulfur, because sulfur is a nonmetal. Nothing's going to happen to it. It's not going to react. So you need to make sure you understand the separation techniques that need to be used, or you're just wasting your time. And what type of have enough knowledge to know which technique is going to work with what component you have. There are 4 listed in your PDF, but there's actually 5 that are used in this lab. The 4 here are listed in the PDF, and I put a little summary to each, but I'm going to break them down into more, explain them a little better on the next page. But they are decantation, filtration, extraction, and sublimation. All, if you were doing this in the lab, all of these would be used. So the first one I'm going to cover is filtration. Pour a mixture through a filter. So you have a mixture here that's a solid and a liquid. You will pour that completely into this funnel, so you don't want to leave anything in this beaker. And the solid will get stuck at the top, so it'll be filtered out. And the liquid will pass into the bottom container. And we use filter types, and there's different sizes. They're not paper, but they're kind of, I don't know how to explain them. They don't fall apart easily. They're meant to be wet. They're meant to filter, but they also are gentle enough that if you poke them enough, you can, they're kind of like, I don't know, but they're not exactly paper. They're not exactly cloth. There's a mixture in there that kind of keeps them a little sturdy while they're in a filter. I've never once considered what they were made of, even though I've used them many, many times over the years. And then you would place it in a funnel and then allow the liquid to pass through. And depending on what you want, in some labs, you may want the solid and you would discard the bottom. And in other labs, you want the liquid and you would discard the solid. The next one is an extraction. There's different types, and if you go into organic chemistry, you'll learn more about this. But in this case, it's a liquid-liquid extraction is the easiest one to explain. So for this lab, and I'll go into it again, but the easiest way is to kind of bring up some of it now. Once we remove the ammonium chloride, you're going to have a mixture of sodium chloride and silicon dioxide, the sand. You need to separate them from each other. Well, how's an easy way to do that is with water, because the water will dissolve the salt into its substance and then leaving behind the sand. So that's an extraction. You've pulled one component out, leaving the other one behind, because the water is not going to really do anything to the sand, but it's going to remove as much salt as it possibly can. So this is dissolving one substance into another, leaving the insoluble substance behind, in this case the sand. The sand is insoluble. It's not going to react with the water in any way. Next one is decantation. This is when you have a solid liquid mixture and you let it settle. So this takes a little while. You need it to completely settle out so the solid will sit at the bottom. Then once it's sitting at the bottom, you very carefully and very slowly, you don't want any vibrations or movement, you decant the water, in this case this water and sand. You pour the water or liquid into another beaker and you leave the solid behind and you try to remove as much as you can. You need a little patience to do this carefully, but this is decantation. Separating liquid from a solid, removing liquid when the solid settles. So you would take the top layer and leave the bottom layer. The next one is evaporation. So this goes hand in hand with extraction. We have our salt water, and now we need to remove the water and keep the salt. How do you do that? Evaporation. You pour this into an evaporating dish, which, by the way, never do it this way. You should always have your solution strictly in the evaporating dish. and prepare to have it over the Bunsen burner. This will evaporate it away. Let's pretend this is salt water, even though it's, yeah, salt water, but NaCl and water, not ocean water. It'll be kind of clear, maybe a little white. And what it'll do eventually is if you evaporate it away, it's going to look like this. It's going to have salt crystals and all the water will be gone. So that would be evaporation. So you recover what you took from the extraction and remove the water again. Sublimation is when you have a solid and it passes straight to a gas. You never pass into the liquid phase. And that is what happens with ammonium chloride when you bring in a certain amount of heat. It will sublimate away into a gas and therefore bypass the liquid phase. Which leads us to the step of this lab. So I always will do a summary or an overview of the steps, but I never go into exact details. That is what your reading is for. And I strongly recommend you always read your labs, the PDFs completely, and maybe even a few times. So here you have a mixture. So you start out with the mixture. The first step is you want to remove the ammonium chloride. So you're going to heat this, but this heat is not going to remove the salt and it's not going to remove the sodium dioxide. It's not even going to do anything to them. But it is hot enough that it will sublime the ammonium chloride away. And then you're going to measure the loss of ammonium chloride to determine how much ammonium chloride you had in the mixture. The next step is now you have ammonium chloride gone. You are going to now have sodium chloride and sand. You are going to, the second is an extraction. You're going to separate these two. How do you do that? You do that by adding a certain amount of water, and that is going to pull the sodium chloride away. It's going to leave the sand, and you're going to have sodium chloride. You are going to evaporate the water away, and when you have dry and cool sodium chloride back as a solid, you'll weigh that. And then on this side, the wet sand is what's left over, and you're also going to dry that. You're going to heat that to constant mass, meaning you will heat it until you have less than a 1% difference in the mass. After it's been cooled, you'll put on the balance, you'll check the mass, you'll come back, heat it maybe for 5 more minutes, and when the mass stays the same on the balance, that's constant mass. You are done. And then that's the same thing. You'll weigh this out. So this, if we were to do this in person, this is not a difficult lab. You have 4 sections to it. The first one is determination of ammonium chloride. Second is determination of salt. Third one is determination of sand. And then your overall results, putting them together. So here's the first one. Here is what you would have to, you were given on some of them, and the ones that are in bold are what you actually have to answer. I have these listed as they are in your PDF. So as you read, you will see numbers next to them, and this goes with your reading. So if you don't understand, for instance, what number 3 is, if you go back to your procedures, you'll find this number 3 in brackets, and that is exactly in the instructions or procedure that they're talking about it. So you can refer back to that. So they gave me this information. Of course, I changed my numbers a bit. And keep in mind that everything that I give you guys is maybe not the values will match what you have, but I follow sig fig rules, I follow rounding, and the numbers, the sig figs that I provide is what was counted right on LabFlow for me. Okay, so I want to point out something here. You have 2 and 3 are very different. You have massive evaporating dish, you have massive evaporating dish and original sample. So if you subtract these 2, it'll give you the amount of your sample, which is right here. Number 3 is mass of evaporating dish after subliming. That means that after ammonium chloride, has been removed. It's gone. It's no longer in the sample mixture. So you need to know what the difference is that has left. That what has left your mixture is actually the mass of ammonium chloride. So I also put up these little brackets so you can see what the steps are that you need to do. So in this case, you need to subtract 2 from 3. This is the mass of evaporating dish and original sample. And 3 should have a smaller amount because the ammonium chloride is gone. and then you subtract those, giving you the mass of the ammonium chloride that left. Now, on your last page, right before your data report in the PDF, it's giving you a formula. You're going to use this formula throughout this lab. We want to have a percentage breakdown of how much was recovered from every mixture. So after you do a technique, we weigh that component out, and we want to know how much you were able to recover from the original sample. So you're going to compare, you're going to add these up for each component, and then you're going to compare it to the original sample as a percentage. If it doesn't make sense, let me give you an example. So I determined that my mass original sample was 0.95 grams. I determined that what I lost, my mass of ammonium chloride, was 0.250. So what I did is you take your grams of a component and your sample mass. So percentage is always, the bottom is always, think of a pie. It's the whole pie, and the top is either slices. How many slices are you dividing into from the pie? So in this case, we're taking our sample mass of ammonium chloride, putting that on top, and we're dividing from our whole original sample. I didn't put the units here because it would cancel out anyways. So out of this mixture, 26.3%, based on what I got from my lab, was made from ammonium chloride. Okay, and this here is not ammonium chloride, but this is a good example of what happens when a substance goes from a solid to a gas and not into the liquid phase. The next one is a little easier. You have a mass of evaporating dish 2, mass of a watch glass, that looks like a little coaster kind of thing, and mass of an evaporating dish, watch glass, and sodium chloride. So you need to subtract these. So I didn't put it here, and sorry, this is a mistake. I didn't realize I had that. You would take 6, subtract 5, and subtract 4. So basically you're subtracting all of the instrumentation or glassware to determine how much of your sample you recovered. And that's what you do here. You have your number 6, this is number 5, and you have number 4. And that's going to mean that you recovered your mass after the experiment is 0.552 grams of sodium chloride. You're going to use the same formula that you used here in the box with the same original sample mass. So this is the mass of the original sample you're going to use throughout this lab. So I have my mass, set that up. I have my mixture was made up of 58.1% sodium chloride. So now I know that I have 26.3% of my mixture was made up of ammonium chloride, and sodium chloride made up 58.1. The easiest thing now would just be to subtract, but you actually need to know the amount. So I would suggest always just go through the whole thing. Now we need to know the determination of sand. So on this one, you have your mass of evaporating dish, and you have your mass of your sample and evaporating dish, and you're going to subtract them, which leaves me with a mass of 0.144 grams. Set this up in the same way, and mine ended up being 15.2%. In theory, your percentages should add up to 100. In reality, never happens. You either have a very low percentage or even over 100% percentage. It's never really ever 100%. That's just not in lab, but maybe on paper. D is a summary of the experiment. So here I have, there was no numbers on these. Mass of the original sample, which is, remember I told you in black, these are things that would be asked for. Experimental mass recovered. That means you're adding up all the masses, and I broke it down over here so you can see. You have your mass from the ammonium chloride that you recovered, you have your mass of sodium chloride that you recovered, and you have your mass of sodium dioxide that you recovered. Add those up. That is what is being asked here. Differences in these masses, and these are absolute values, so you will not have any negative values. So I subtracted this, and I have a very small difference in these. Then I did my percent recovery. So here is mass recovered. I have my mass of the original sample before the experiment, and I have my mass after the experiment. And I set that on top. My mass recovery is 99.6. Now keep in mind, I changed these numbers from the data points that LabFlow gave me. I also changed my results a little bit. So do not worry if when you do this, it doesn't match mine. I changed my numbers so a student wouldn't get my numbers. Just keep in mind that go with whatever your numbers say. If you check and recheck, don't worry about it. You did the lab right. LabFlow, I have found, actually kind of makes experiments not 100% perfect because they want to test your knowledge to see what happens. So your mass recovery may be over 100%. It may be a lot lower than 100%. These are things that will happen. Don't panic. Why am I telling you that? Because on the last page, there's a question and it's got many possible answers, and you need to make sure that you understand it, which one you need to pick. So what happens if you get 100% recovery? For mine, I actually would not say that I was at 100% because I'm not. So I would have to give an answer as to why I didn't get 100%. But if you do get 100% or close to it, I'm not going to tell you how to pick on these. You'll have to decide on your own. What happens if you get 100%? That means you recovered everything. Even after experiment, you had no difference in the original sample mass and the recovered sample mass. What if your recovery is lower than 100%? Well, one of the things can be that your sodium chloride solution, if you've not done this in lab, and I don't remember if Chem 10 did this, what happens with sodium chloride solution is that as it heats up, it pops out and you lose salt all over your bench. That is why you tend to use a watch glass. This is not heat resistant, but it sits right on top of here and it's supposed to help prevent a lot of the salt coming out. And then what you do is you rinse this back in here and then you evaporate it again on a lower heat, and you keep doing that till you can recover as much as possible. Let's say you forgot to put your watch glass on. Then that means that most likely you're going to start losing a whole bunch of salt. It's going to start jumping out, and your mass now that you recovered is no longer the actual amount. So for instance, if we go here, I recovered 0.552, but what if I had a lot of salt jump out? Then that means that after I checked everything, this is no longer going to be that. It's going to be a lot lower, which when I add these all together, means that my total mass is going to be lower. So the salt mass is lost. It's going to mean your recovered mass is lost. And then when you do the percentage and set it up, you're going to have lower than 100%. What if your recovery is higher than 100%? And that does happen. It does, absolutely. This means that when you had to evaporate the water from the sand, you may not have dried the sand completely. And that means that the water is making the sand heavier. So when you do the mass, there's way more mass than it should be. What does that mean? So if we look here, this means that this mass here, I didn't dry this completely. So this mass that I account for is actually going to be way more than this. So when I add it here, this mass is going to be way higher than it needs to be. And then I'm going to account here, and it's going to push this to be over 100. So those are possibilities and things that happen in the lab. In my other, where I teach elsewhere, we do work with sodium chloride solutions, and this happens a lot. Students don't either dry things enough or they lose their solutions, and it's very normal for my students to get over 100% or way under 100%. Never exactly 100%. I don't think that's ever happened. Anyway, so these are scenarios. Read the questions carefully. There's other variables here, so you need to make sure you're actually picking the correct one. Tips: follow sig fig and rounding rules for all sections. You only have one attempt to answer. I do not fix. Once it's in, it's in. I will never go back and help you with an extension. You need to take your time and be careful. I noticed that students jumped on doing lab this week early. I think that's fantastic because you guys can help each other. If it's something that needs to be addressed to me, there's time. Especially because in a couple weeks, we're going to have 2 labs a week. So it's better that you start with the mind frame of tackling one Monday and then maybe tackling the other one Wednesday, complete it by Thursday. So if there's problems, you can address it the Friday morning. Okay. Upload your calculations when requested, must be legible, clear to read. I will deduct if they're not clear. If I can't make out what you did, that's a problem because then I'm not sure that you did the work. Try not, I mean, not that I can verify anyways, but if I can't read it, you don't get credit. Try not to complete on Friday, but early in the week. I think I've already discussed this. If you have questions, I think that I really like that I'm seeing students post and students responding. As long as I keep seeing that, I may hold off on harmonic discussions. But if I see students post and people do not respond, even with, hey, I don't know, but let's try to work it out, I'll bring back harmonic discussions. I am not trying to be mean. I'm trying to get you guys so comfortable with each other that you don't even think twice about wanting to help somebody else out. That is the whole point. Um, I like that because I can always give you the answer, but you're not learning it from me. You guys learn from each other. Chemistry is rarely passed by yourself. It just, in my experience, very few people actually do that well on their own. And since we're all at home, or most of us, this is also an opportunity for you guys to communicate with each other. I have the Pronto app open on my phone Tuesdays and Thursdays. So if you need me, I'm available. And you need to make sure that you indicate it's to me. So if somebody just posts something in general, I may not acknowledge it because it may not be directed at me. And I don't want to answer problems that students can answer. So make sure you address it to me. I don't think it'll highlight it, but because I have my phone app open, I'll be able to read the problem or whatever question and then respond. Okay? So that is it. That is the end. Have a good evening.